Well, good evening, everybody. My name is Cyrus Rustomji. I'm co-founder and chief science officer over here at South 8 Technologies. I'm excited to kind of share with you a little bit about the work we're doing here, exploring these liquefied gas electrolytes for advanced lithium-ion batteries and bringing them to market. So, quick overview of South 8. We are a startup out of UC San Diego. We spun out in 2016. We're located in Paradise on Earth, as I like to call it, San Diego, California. Today, we're about 45 employees, great diverse team over here as well. Our IP portfolio consists of 27 issued patents across 22 different patent families, and always growing that IP portfolio. Our intellectual property really covers your liquefied gas electrolyte formulations, the engineering around the injection, the cell hardware, as well as methods of manufacturing. I'm getting a little audio feedback. If everyone doesn't mind muting themselves, that'd be fantastic. Thank you. We are leveraging a wide base of suppliers, specialty gas manufacturers, with potential to source exclusively from domestic facilities in the future. So pretty much our entire supply chain is really based here in the US and in North America, which is going to be extremely important as we move forward with kind of lowering our reliance on our Asian friends across the pond there. And for development, we are actively working on a lot of contracts with the DoD, automotive manufacturers, power tools, et cetera, et cetera. And what's public out there in terms of our investors, we have LG Energy Solutions on the cap table, Lockheed Martin, Porsche Ventures, as well as several other great names that are all shown here. And really appreciate all their kind support over the years. And I was actually asked to encourage everyone to turn on their video and audio. I forgot to ask that at the forefront. So if you can all turn on your video, but maybe mute yourselves for your audio, we'll save a little Q&A for the end of the session here. So let's get into it. As a kind of a high level, the U.S. is behind in cell and electrolyte manufacturing today. The U.S. is only, I think, has 60 gigawatt hours of energy, where China is really kicking our butt there, producing closer to a terawatt hour, I believe, these days, in terms of cell manufacturing capability. I'm sorry, there's a lot of audio feedback. Can everyone just mute themselves? That'd be great. Thank you.
Hi, Gregory. Can you mute your mic?
Thank you. Perfect. We did it. Excellent. Thank you, everyone. So in terms of electrolyte manufacturing, we are very far behind in the US, producing only about 2% of the global manufacturing capacity for electrolyte. So my question to the audience today is, how does the US really secure our electrolyte supply chain and stay in front of the innovation curve? The Biden infrastructure law has provided a lot of resources to scaling up manufacturing, but a lot of this is Me Too products, basically the electrolyte that's already being produced today in Asia, specifically China. Same thing with cathode, anode, separators. So we really want to innovate on that and stay ahead of this innovation curve. One area that we can really look at is the established gas industry to leverage their already existing manufacturing operations to enable our rapid innovation and scale. So if you look at that gas market, they're about $130 billion today, compared to the lithium-ion cell market, roughly 50, or maybe I've seen reports up to $100 billion today on the cell level. The electrolyte is a very small component of that. And if there's a method where we could actually leverage this very large market into the electrolyte industry, that already gives us economies of scale to bring the cost very low. And I'll explain today to you how we can maintain and improve upon performance within your lithium-ion cells for these growing markets. So what is South 8 really focused on? We are working on a novel liquefied gas electrolyte that is more or less a drop-in replacement for your current cells today. So of course today we are all using these liquid-based electrolytes in everything from our cell phones to our EVs and energy storage systems. It's basically a fluid in there that we sprinkle a little salt in, and it becomes an ionically conducting medium. Now, I say fluid specifically because a liquid and a vapor are kind of actually fluids. We all know that vapors can also be liquefied under a moderate amount of pressure into a liquid phase. And so what we've actually been doing here at South 8 is taking these gaseous products that we know at room temperature and standard pressure that are gaseous, liquefying it under a little bit of pressure, and then putting it into a cell. Think of propane for your barbecue grill. Propane is a gas at room temperature and standard pressure, but you can liquefy it under a moderate amount of pressure and store it inside a tank underneath the grill. That's essentially what we're doing here. We have found a unique class of electrolytes, though, that work very well inside. A unique class of gases that work very well inside your lithium-ion battery. So we did some early work out from UCA San Diego, exploring some of these liquefied gas solvents. And again, it works just like a normal solvent would. It is a liquid phase under pressure, which we add some salt into. So here's your little diagram of your lithium salt cation, your anion shown here in red, and then your green solvent molecules. That's essentially what we have here. Over here on the right, we have a chart that is showing some DFT calculations, showing your ionization potential, which is another way to look at your oxidation stability. And over here on the y-axis, your electron affinity, which is another method to look at your reduction stability. So essentially your stability on your anode shown on your y-axis and stability on your cathode shown in your x-axis. We ran these calculations for a number of liquid solvents shown in blue and a number of liquefied gas solvents shown in red here. I include CO2 here shown in green. Don't ask me why it's in green, it just is. Pretty much the idea here is to move to the upper right section of this chart. The more to the upper right you go, the more stable that solvent is electrochemically, and it can perform a better cycle life than you would if you were less stable. Now, of course, you want to form stable SCIs and CEIs, and that kind of comes into a lot of the tricks that we do here at South 8, of course. I highlight fluoromethane up here in the upper right, because that is pretty much the only publicly disclosed lead gas components that South 8 has developed. In the literature, you'll see other gases that we've worked with in the past at UC San Diego. That's not necessarily the direction that South 8 is taking. South 8 is taking kind of an approach where we want to lower as much as possible the global warming potential of these solvents, lower the cost, and ensure domestic supply chain with the cost that the components that we procure. So having established that, okay, these gases are electrochemically stable, what are some other qualifications that we look at for selecting our gases? Well, we want things that are cost effective. So we really just look at commodity gases. So think, standard gases that you could buy off the shelf today. Pick up the phone, call up Air Liquide or Praxair or whoever, and have a cylinder delivered to your door the next day. That's essentially the components that we're looking at. We always want to look at low viscosity and low melting points. That ensures good low temperature performance. We work with exclusively non-ozone depleting, non-toxic, and non-corrosive components. So anything acidic or that can be corrosive or toxic, we do not use. We do use some low global warming potential components, but these are significantly lower than your standard refrigerants. And so we are aiming to be very compliant with all the new regulations that are coming out. Of course, I already discussed electrochemical stability. We want these solvents to be very stable in your battery cell device to ensure long cycle life. And I already mentioned these are commercially available in high purity, of course, and of course compatible with all your common battery materials. So we use all your standard anodes, cathodes, separators, binders, current collectors, all these items our gases are fully compatible with. So it's essentially a drop-in replacement for that jelly roll. Here on the right is a standard vapor pressure curve for a typical electrolyte that we use today. At room temperature, we're operating right around 300 psi. And around 100 degrees Celsius, we are looking to vent the cell. That allows us to kind of operate with a good buffer between 60 degrees Celsius, where it's kind of the max operating or storage temperature, and before where we hit thermal runaway, closer to like 110, 120 degrees Celsius is generally where you see things really take off. So by venting the cell at 100, we can kind of cut off that thermal runaway reaction, but still maintain very high performance in the cell applications and with our customer requirements. So this slide is showing pretty much all the different value propositions that we have here at South 8 with our liquefied gas electrolytes. I'll kind of touch on all of these through the following slides, but we do offer improved safety through a reduced fire risk with minimizing the potential for thermal propagation in your battery packs. Wide temperature range, industry-leading performance, everything from -60 to +60 degrees. I've already mentioned material compatibility is no problem for us. We do offer increased energy. We are compatible with silicon anodes, but we can also go to thicker electrodes and higher voltage cells as well to increase your cell energy. We also perform very well under fast charge requirements. And lastly, it's a very cost-effective solution. Again, we're using commodity components, so we don't have to worry about manufacturing or synthesizing any new materials. So these are all very low-cost materials that we're using today. So the Gas Electrolyte is a platform solution, and we are fully compatible with all your conventional cathodes, anodes, and separator materials. I mentioned that a few times already. One thing I will note is the form factors which we're operating in today. We're essentially just focused on cylindricals. 18650s and 2170s we are already producing and sending out to customers today. The 46XX packages is something that we're developing, and we hope to be shipping out in the very near future. Call it early next year. Those will start going out the door as well with some of our partners. Okay, let's get into some data. This is where all the excitement really happens, I'm sure, for a lot of you on the call today. So we want to share some data on this is a 2.7 amp hour 18650 graphite anode NMC811. So you're run-of-the-mill type lithium ion cell today. Over here on the left, we're showing a power map at room temperature. We charge these cells at a C/3 charge rate and then discharge at various rates from C/10 to 3C. And you can see our liquefied gas electrolyte can handle these increased rates without any problem, still achieving close to 100% discharge capacity at those higher rates. You can always expect a little bit of voltage drop there with the electrical impedance and things like this. On the temperature map, we are charging these cells at C/3 at room temperature, but then discharging across all these temperatures. So everything from 40 degrees Celsius down to minus 60 degrees Celsius, we're operating very well in. Now, as we all know, that lithium ion cells with your liquid electrolyte begins to lose performance right around 0 degrees Celsius. By minus 20, you're really losing everything if it's not already frozen. But anything below minus 20, you pretty much lose all your power and capacity in that cell. Unless you have some specialty electrolytes, which some people have developed. Here at South 8, low temperature is never a problem for us. We go down to minus 60, still delivering about 70% of your capacity on this specific cell design. We've also developed some silicon chemistries, which deliver even further improved performance down to minus 60. Now, while most people only need minus 20 or minus 40 degrees Celsius, we offer improved performance at those temperatures. But for those really extreme applications down to minus 60, we're really the only game in town. For those, we're really talking aerospace, NASA type applications, and defense, and some other opportunities out there as well, which we're looking into. For cycle life, these cells have been charging and discharging at 1C. And this plot needs an updating. I think this is actually outdated data. But anyway, we can go well past 1,000 or 2,000 cycles at the room temperature, no problem at all. At higher temperatures, we are projected to hit about 1,000 cycles there, so pretty good up to 45 degrees Celsius. And then at 0 degrees, this is pretty typical for lithium-ion cells. They cycle pretty nice at 0 degrees as well, but it's pretty early in testing for us there, and so we'll update this data hopefully soon. This is the same cell package, but now it's third-party data that we are sharing with you today. So we have 2 jelly rolls, both 18650s, one filled with a liquid electrolyte, one filled with your gas electrolyte. And the liquid electrolyte is just your run-of-the-mill type carbonate-based electrolyte, nothing special there. This is just showing fast charge cycle life, where this is a DOE protocol, I should add. Every 3 cycles, it's a C/3 charge and discharge. Every 4th cycle, it's actually a 3.2C, which is equivalent to an 80% state of charge swing in 15 minutes. And you can actually see that the gas cell is outperforming the liquid cell. We believe this is primarily due to the improved conductivity and the lower SCI impedance we have on the anode. So that allows less lithium plating on that anode and faster diffusion into the anode during these fast charge protocols. So we all know during fast charge, it's really the lithium plating that will kill you and kill your cycle life. So we actually mitigate that with the lower impedance SCI layer on that cell. Here's just your typical cycle life at C/3 charge and discharge, outperforming that liquid electrolyte. If you buy a commercially off-the-shelf cell from Samsung or Panasonic, this liquid electrolyte curve would be better, But this is actually just an R&D cell we procured from some partners at a low volume. So that's probably the reason why your cycle life on the liquid cell is not as great. And then at 45 degrees Celsius, we do have pretty much on par performance with that liquid electrolyte cell. So pretty good performance there at higher temperatures. Moving on to silicon. This is some work we've been doing with a partner. These are 3.2 amp hour cells, 18650 cell form factors with silicon into the graphite matrix and an NMC cathode. So power mapping this up to 1C is no problem for us. We can do power all day long. That's not an issue. Temperature map, everything from 45 degrees to minus 60. Again, looks great with these silicon anodes. And we haven't started fast charge testing with this yet, but we do believe the fast charge will be improved with the silicon cells as well. And then on the far right, we have cycle life, both stacked right on top of each other, the liquid and the lead gas cells there. So very good cycle life with those silicon cells as well. So just showcasing some of our other abilities. This is an LFP cell with a graphite anode, fairly low capacity, only 1.4 amp hours. Again, these are just R&D cells that we're procuring. Good power capability, everything from C/10 to 3/C, delivering pretty much 100% of your nameplate capacity. For temperature mapping, you can kind of see a recurring theme with the power, temperature, cycle life. I try to keep it all standardized for you to keep it easy. For the temperature mapping, going from plus 60 to minus 40 is no problem for us. We all know that LFP is a pretty decent power electrode, but you have to nanosize those particles. But inherently, the ion mobility in LFP is actually lower at low temperature. That's due to the one-dimensional olivine structure in that cathode. And so we actually do see performance drop at low temperatures more than your NMC cathodes. And that's very much highlighted here, where at minus 40, we're actually taking a pretty good hit. And at minus 60, we just don't see any performance out of this specific cathode. So we are looking to procure maybe a better quality LFP to integrate into these cells and improve that low temperature performance. So as the automotive industry is adopting LFP as the go-to cathode, everyone's looking for lower temperature solutions. And so this in the future, we hope will be a good one for everybody. And on the far right, we're just showing 1C charge and discharge here, overlaid liquid and lead gas at 25 and 45 degrees Celsius. And looking pretty good there as well with these LFP cathodes. So of course, one of our differentiators in the market is our low temperature capability, in case you haven't guessed that yet. There are a lot of people asking for rechargeability down below 0 degrees Celsius, which is the limit for your conventional liquid-based electrolytes. And so we are doing a lot of work with partners right now to demonstrate rechargeability at lower temperatures. And today we've demonstrated essentially a good C/3 charging at minus 20, which is pretty nice. So you can see here kind of a little temperature bar graph here. At 0 degrees Celsius, you can see liquid and lead gas perform similarly well, kind of 99.9% your Coulombic efficiency during charging and discharging at the C/3 rate. When you get to minus 20, you see a pretty considerable drop for your liquid electrolytes. That's really due to all the lithium plating that's starting on your anode, which decomposes your electrolyte and kills your cell pretty quickly. Yet lead gas still maintains very high Coulombic efficiency at minus 20 at the C/3 charge rate. Then you go to minus 40, and we do see a little bit of a drop with our lead gas electrolytes. So we kind of cut off the kind of on our spec sheet, if you will. Minus 20 is kind of what we can do. Minus 40 is kind of hitting that danger zone, if you will, with our current with our current cells and electrolytes. But you can see the liquid electrolyte just drops out completely. You get no charge or discharge with those liquid electrolytes. And so some current efforts we are working on with our partners is moving to lower temperatures at increased rates. And so we will see what we could do on some of these projects. And again, silicon is one avenue to actually improving those rates. And so we are very much looking forward to achieving our future goals here to meet customer requirements. So a few other areas that we are looking to increase energy, silicon, of course, but also going to thick electrodes is really interesting to us at South 8. We believe we can offer a 7% increase in energy and a 7% reduction in dollars per kilowatt hour with thicker electrodes. So why can South8 enable these thicker electrodes? Well, if you imagine your liquid electrolyte, it's a more of a higher viscous solution. When you add it to your these thicker electrodes, it doesn't wet that entire electrode very well. It leaves a lot of gas pockets. You don't really get the power you really need out of that cell, and your cycle life kind of just goes kaput very quickly. With South8's lead gas, the lead gas solution has a significantly lower viscosity, probably about an order of magnitude, which enables very good wettability into those electrodes. On top of that, we're injecting these solutions under pressure. Into the cell, we inject under pressure, which allows us to penetrate those very thick electrodes into every small little nanopore within that electrode. And lastly, we still maintain a very good electrolyte conductivity, so we can maintain that high power performance that everyone knows and loves. So this chart on the left is really showing your cathode thickness, and you would pair that with an anode, of course, of appropriate thickness. Your liquid electrolytes is really limited to about 60 to 80 microns. But with our lead gas solution, we've kind of modeled it out. If we can bring this up to about 180 or 200 microns, you can kind of see how the gravimetric energy follows this curve here. We can offer a considerable improvement in energy just by thickening up that electrode, which also reduces your cost at the end of the day. And this is easy for us. We've demonstrated thick electrodes up to 200 microns. It's no problem. So we are working with partners today to really procure these thick electrodes in a higher volume, so we can start making these cylindrical cells and building and demonstrating the higher energy and reduction cost potential there. So looking forward to actually demonstrating this in the very near future. Other areas we can actually reduce the cost. So there's this high voltage spinel cathode, LNMO. It is a cobalt-free cathode with very low nickel. It essentially has the same cost of LFP, but it's more closer to the energy of NMC. Like it's kind of the energy of NMC 622. And further, lead gas can actually drop the cost even further. So this chart on the right is kind of showing you the breakout of what your typical liquid electrolyte cost is in a gigafactory, essentially. And you can see how we drop the cost moving from NMC, about $54 per kilowatt hour, to LFP and LNMO. And this all kind of, as you turn the knobs, you can see how LFP and LNMO is a much lower cost than your NMC. Everybody knows that. With a lead gas electrolyte, we can actually drop the cost even further. I won't get too much into a few of these items, but we actually can eliminate the need for dry room when we're filling the liquefied gas electrolyte into our cells. That's because we actually seal the cell prior to our electrolyte injection. And we just have a tiny little hole, which through some mechanisms is sealed until the injection process starts. And so we can actually eliminate some of that dry room requirement. I just discussed using thicker electrodes to lower the cost. And also we have demonstrated faster formation times. So whereas today a lot of people are forming the cells in days, not hours, South8 has already demonstrated we can indeed form our cells much faster. You can understand this through the gassing process that occurs during your formation process. Those gases can actually block your electrode, and so you have to wait a very long time for those gases to diffuse out of your jelly roll to the surface to allow the electrolyte to re-wet that surface and continue to build that SCI layer. With the lead gas electrolyte under pressure, these gases are not really formed. If any of those molecules are formed, they just solubilize right into your electrolyte. And so you can accelerate your formation timing considerably there, which is very nice. So I did want to take a minute to speak about our LNMO efforts, because we do have an RPE project ongoing, which is geared towards this high voltage cathode, which has the promise to reducing EV costs in the future. So again, on the left, we are looking at our power map. The high voltage spinel is well known to have a three-dimensional kind of ionically conducting structure, which is a very good power cathode, essentially. And so we've only gotten to 1C with on this test anyways, but very good performance there, showing 100% discharge capacity. The temperature map is great. Going down to -60 again is no problem for us. And the cycle life is really interesting. Because it operates at a higher voltage, your liquid electrolytes always fail very quickly because your standard carbonate-based electrolytes just do not withstand that high voltage, and they all begin degrading and the cell will fail very quickly. So you can see within tens of cycles, you hit 80%, and then very quickly it's diminished to essentially nothing. With your liquefied gas electrolytes, on the other hand, it is a little odd. We have this quick drop down to 80% discharge capacity, but then it levels out thereafter. Internally at South 8, we're better understanding what this mechanism is, and we have identified some paths forward, which we are currently developing. But the fact that we see this really nice plateau over here, where it's relatively stable, just tells us that these liquefied gas electrolytes are more inherently stable than your liquid counterparts. And we are excited to actually share some future data with you showing that we can actually take this plateau and elevate it back up to closer to 100% and really enable this cathode. So this is early work, but it's very promising in the direction we want to go. So stay tuned for more on that one. I hope I'm doing okay on time. I want to make sure I leave some for Q&A. But quickly, I will just speak a little bit about safety. Essentially, here's a kind of a map of heat generation on the y-axis, kind of qualitatively speaking, and then mapping that with temperature. You have your normal operation up to about 60, 70 degrees, which thereafter you start begin seeing SEI decomposition. And then once you get hot enough, you start to get solvent decomposition on those anodes and cathodes, which really drives your thermal runaway reaction until your separator melting point, right around 150 degrees Celsius, which then short circuits your cell, drives thermal runaway. With the liquefied gas electrolyte, we have a really unique capability. If we're able to vent that cell of all of our electrolytes right around 90 or 100 degrees Celsius, we remove a lot of that fuel for that reaction and shut down ionic conductivity. So by shutting down ionic conductivity, we can actually stop the temperature increase due to all those exothermic reactions and really prevent a lot of these thermal events from occurring. And further, by removing that fuel, if there ever was a thermal event, then the heat output or heat generation would be substantially less than your standard lithium-ion cells. So essentially, the less fuel equals a safer cell. And some of our testing to date really demonstrates that fact. So here's a quick test on what do we have here? A 2.7 amp hour, 18650 graphite anode NMC cathode, nail penetration, where we compared two jelly rolls, one with liquid electrolyte, one with South 8's Lee gas electrolyte. When we drive this nail through the can, we can actually see the peak temperature of the liquid electrolyte hit 700 to 800 degrees Celsius, whereas the South 8 cell was considerably cooler, right around 400 degrees Celsius. And of course, this is a dead short, didn't give much time for the cell to evaporate all those the solvents out of there, so you do see a thermal event, of course, but the total temperature is less. And furthermore, we actually looked at, with a thermal camera, kind of judged when the cooling time reached 100 degrees Celsius. The liquid electrolyte took considerably longer, the order of 15 minutes, where the South 8 Lee gas cell cooled down much faster, about half the time. So this really reduces the tendency for thermal propagation from one cell to the next. And we do believe through kind of updated electrolytes that we're working on and modifications of those cathodes, we could even further improve this safety, which is super critical to all of our customers in the industry today. Here's just a few images from South 8 today. On the left, we have our electrolyte mixing pilot system, if you will. So today we have 8 different gas lines. You can kind of see that in the image here, 8 different verticals here. We just kind of go to the software, type in exactly what formulation we want, click go, and it fills a big keg of electrolyte over here on the left. That keg is about a few liters large, where we can fill hundreds of cells with. We bring that keg to our Lee gas injection system over here on the middle image. And currently today, this is a single cell injection system, but it's a very rapid process, which we're able to inject our cells. And we are actually developing a multi-cell injection system to be in-house early next year, and then delivering to our cell manufacturing customers very soon thereafter. So today we are developing these 18650s and 2170 cylindrical cells. Holding one in my hand right over here, we actually build several dozens of these per day for delivery to all of our customers. Here's just an animation, if you will, of all the form factors that we're looking at. Everything from a 14500, kind of a AA, all up to your 46XX, which we will be delivering to all of our customers in the near future. And with that, I would like to thank you for your time and really excited to open up to Q&A. So thank you so much for your the opportunity today to discuss. Thank you.